insertion sort is some numbers have been sorted and some numbers haven't been sorted, and you take a number that hasn't been sorted and you put it where it belongs, right? So you keep taking numbers that haven't been sorted and you find out where they go, right? Everybody good with insertion sort?
Yes.
So now the code here that I give, I can imagine it's hard to follow because you have to deal with the heads moving and you have to deal with memory, and I do this allocating memory and deallocating memory, and I do this writing and reading. So I can see understanding the code would be kind of a pain. So I'm going to explain the code to you. And then I just this minute finished making more PowerPoint slides for explaining to you the answers, but I'm not going to give those to you right now. I'm going to give those to you tomorrow sometime, right?
I have one question, sir.
Yeah.
So after line 18, does the code repeat itself? Like, you know, we don't have to write much, or like how? That's what I'm stuck at, because allocating the memory and delocating the memory, it is repeating all the time. Like,
yeah.
Do we cut out like some parts? Like, you know, it jumps. Does it jump
I don't
in
know.
the code?
Why don't we wait until I go through the code and then you
Okay. All right. Okay.
ask some questions.
Sure.
One thing I want to make sure is that I've gotten a number of emails saying that people haven't gotten the test. So if you haven't gotten the test, I posted it on the forum. You can get it from your friends. You can, hopefully everybody has it. All right. So let me go through these slides. Oh, we got a little guy up there. Ignore that little guy. He's not supposed to be up there. So anyway, what's the problem? The problem is insertion sort. What's the precondition is that we have the inputs in different cells between 1 and n. I'm going to put negative infinity in cell 0. Why do I do that? It just makes our code smoother. That you'll see it's smaller than everybody else. So it's sorted, so we'll never go past it. And the head is going to start on cell 1, which is the first number that we need to sort, right? So that's the precondition. The post, oh, here, we went, there we go, here we go. Now, the post condition is that everything's the same except we've sorted the numbers, right? As you would expect. And the place the head ends up in the code happens to be after, on the first blank after the input. So we might as well say that's okay for it to be there. Holler if anything that's on this, don't ask me questions that are off somewhere. But if you have a question about what I'm saying, then holler. All right? So then we're going to have a loop invariant. And what's the loop invariant? The loop invariant, first I'm going to talk about a measure of progress, right? So you can imagine I have numbers that aren't sorted and I keep inserting them where it's sorted, right? So the loop invariant is going to be how many numbers have I sorted, right? I'm going to sort more and more numbers. Now, how am I going to store these numbers are sorted and these numbers are not sorted? How do I keep track of the boundary between these two sets, right? That could be complicated given that I can't store my state a number I and I don't have two heads, right? So I'm not going to remember what's sorted and what's not sorted, right? So here, the loop invariant is going to just be some things are sorted, and the measure of progress is simply let R be have the value that it just happens to be a value where everything between 1 and R is sorted. And then when you go from R to R plus one, cell R to cell R plus one, it's not sorted, right? So I'm just telling you, given our current situation, I'm defining R to be that value. And so we'll use that, we'll talk about that value, right? Does that make sense? So right now you'll see just the way the input came, R is this cell because 6, 8 is sorted, but then when you go to 2, it goes down, right? So that's our value of R. And then what's our loop invariance going to say is that the head, where is the head? It's always going to kind of live between cell 1 and cell R plus 1, right? It's going to have to come over to the 2 at some point in order to know that we're not sorted, in order to get that 2 and insert it, right? But otherwise, we're always living between, and we're not going to go over to, well, briefly, we might pop over to the negative infinity to know that that's negative infinity, but we won't stay there long. We'll come back. So our loop invariant when we're at the top of the loop is that. All right, everybody good with our loop invariant? Oh, there's another thing I forgot to add about the loop invariant. The Turing machine, it can't remember the value R, right? Because R is the number between 1 and n. But we've stated somewhere that the range of the values in the cells are between 1 and d. So we can store in our states the number 1 through d. D can't grow with the input. D is fixed, right? So we can store a value that's on our tape, and so here, so what am I storing? P is going to store the value that's in the cell previous to the head. All right, so currently the head is at cell 1, so the cell previous to the head has the value negative infinity. Right? Everybody good with the loop invariant? So how do we establish the loop invariant? Right? What does that mean? That means suppose we're at the precondition, right? So we're at this picture and we want to get to this picture. Anybody see what do we have to do to get from this picture to this picture?
Create variable P.
Exactly. So the code is going to, the first line of code will allocate memory for the new variable P, and it will set it to be negative infinity, right? That's what the code did, and it establishes the loop invariant. Right, everybody go to that?
So
I just had a question. So do we have to say that? So I understand how it establishes loop invariant, but do we have to say that? Do we have to say that lines 1 to 2 establishes the loop invariant, and then explain how?
No. I was thinking about giving the same question in 3101 next term. Maybe you'll be taking it from me. And then in 3101, you'll have to prove that if the precondition's true and you do this code, then you're going to establish the loop invariant. That's what you're going to do in 3101. But in this code, in this assignment, you don't have to prove anything. You don't have to understand anything. You have to translate it into Turing code.
Okay.
Right? So I'm telling you that we're establishing the loop invariant for 2 reasons. One, my goal is to teach everybody loop invariance, and this is a warm-up for 3101, and you might not take it from me. It's good to know loop invariance. And the other reason is I want you to understand this code, and what the code does is it does loop invariance, right? So everybody say, I tell you what the loop invariant is, and from the precondition, it's not hard to establish it. All right, so now that's just the repeat of the loop invariant. I added here the goal, and the goal, of course, is to make progress while maintaining the loop invariant. And so remember, our measure of progress is R. So our goal is to increase R. And how do you increase R? Well, you find the value that's in R plus 1, right? Because that's the first guy that's not sorted, and you put it where it belongs. All right. So if we do that, then we're back at the top of the loop invariant, and we found R, and we found the guy at R plus 1 is 2. We put 2 where it belongs, and now the Turing machine doesn't know that, but when we look at it, we see, look at R's increased, right? The head could be anywhere in here, but it happens to be on the 2. Why? Because that's the guy we just inserted, right? And so then P, to be the loop invariant, P has to have the value before, which is still in negative infinity. All right. So now let's do it again. We're going to find the value at cell R plus 1, and we're going to insert it, right? So there we inserted 5 where it belongs. Everything else, you see, everything else gets shifted over, right? 6, 8 got shifted over, and 5 got put in, right? Everybody see that? And so do we have the loop invariant maintained? Right? What does the loop invariant say? It says that things are becoming more and more sorted. R is the value that's the last guy sorted. It says the head's somewhere in between, which is true. It says that P is the value just before the head, right? Everybody see that? Now, I'm not really caring where the head is, but I happen to know it's going to end up at the value that we just inserted, right? But that doesn't matter to us. To establish the loop invariant, all we need to know is that it's somewhere in this range, right? Everybody good? All right, then let's do it again, right? What is the guy who's next? The guy at R plus 1 is the 1. So we shift everybody over and we put the 1 in. And so that's not too exciting. The one thing that's slightly exciting is that you'll note R happened to go up by 2, right? Why did it go up by 2? Well, because when we moved 1, that moved it up by 1, but 9 happened to be bigger. And so R got bigger by 2, right? So we made extra progress. Everybody understand this is the big picture, how we're maintaining the loop invariant every time we go around the loop, right? Everybody good?
Sir.
Yeah.
So for whenever we insert, P becomes the value just before where we insert the value?
Yeah. Yeah. So the loop invariant just says that the head needs to be somewhere and that P will be the value before the head. That's what the loop invariant says. Now, as an extra side, I could tell you, yes, the head will be at the value that was inserted. But we don't need to know that. All right, everybody good? All right. So now let's continue on with the code, right? Here's our loop invariant. Here's one example, right? I gave you a bunch of examples at the top of the loop invariant. Here's one we're going to work with. Suppose we're at the top of the loop and this is true. All right. So what does the code do? It goes, line 4 is the top of that outer loop. Oh, no, sorry. Line 3 up here is the top of the outer loop. And the first thing it does in line 4 is it starts an inner loop. All right. So we go from outer loop to inner loop. And so the inner loop is going to have its own loop invariant, right? So we have to understand what the loop invariant is, and we have to make sure that because this loop invariant is true, when we get down here, this loop invariant will be true, right? If this is true, then this is true. Does that make sense? All right, well, let's look at our picture. Let's look at what is the new loop invariant. Well, actually, it's not going to be hard to maintain it because it hasn't changed any, right? Our loop invariant just says, hey, we have the same loop invariant as we had before. Since our initials, where the values are, whatever values we have in this at the top of this loop, this is going to be the values we're thinking about. And right, so the values haven't really changed, but what's changed is we might have moved our head forward, right? So nothing's changed, everything's good. All right, so let's say maintain this loop invariant. Suppose we have this loop invariant. Now we're going to go through the inner loop. All right, here's the inner loop. What happens when we go through the inner loop? Well, the head moves, right? We need to make progress, and how do we move progress? By moving the head right, right? So every iteration of this inner loop, the first inner loop, is going to increase I. I is where the head is, right? So here, look we moved I forward. And when we moved I forward, we made progress, but we also have to maintain, right? We had to remain the previous loop invariant that P is the value before the head, right? So here, the head was here, so P was 2. Here, the head's here, so P is 5. Everybody see that? That's what the inner loop does. We do the inner loop again, we move forward, right? So, oh, that looks like a typo. Typo, we don't like typos. There, that typo we fixed. All right, everybody good with that? So, so now let's start writing the code for this inner loop. And I'm not giving it all to you. We'll give some of it to you later. I'll give it to you as we explain it, right? So here's this inner loop starting at line 4. And what do? We say, well, let's see donate the value that's at the head, right? So currently 8 is at the head. So C has the value 8, right? And then what do? What we're going to do is we're going to move the head right, right? So the head's going to move right. And when the head moves right, then P needs to remember the previous value, right? So what we're going to store before we move the head right, we're going to save in P the current value. So when we move right, it has the previous value, right? Everybody follow that? So this code is pretty straightforward, right? You run this code, it maintains this loop invariant, right? It says my head's here, so I save the 5 in P and I move my head here. I'm here, I save 6 in P, I move my head here. I'm here, I save 8 in P, I move my head here. Everybody good with that? So you run that code and we'll get here. All right? Everybody following the code? All right, so the next thing to do is, well, we got to stop at some point, right? We need an exit condition, and I haven't told you the exit condition yet, but one of the loop invariant requirements is that I is between 1 and R plus 1, right? Look at our head, I is the head. Our head has gotten to R plus 1, right? So we can't move any further right. This is where we want to be. Why? Because we want to take that 1 and start going left again. So we want to stop here. And how do we know that we can stop? Anybody? You have the code maybe in front of you, but just watch a slide.
When it reads a blank, like when the head reads a blank?
Certainly, if we got all the way over to the blank,
Yeah.
then not only would we stop this loop, but we would stop. Right?
It would halt.
If we can run all the way through here and it looks sorted, then we would say the program's sorted. But how are we going to stop this little loop, right? I'm not looking at a blank. What do I know? Right here locally, what values do I know?
Less than P. The value you're pointing at is less than P.
Right, I know the value 1 because it's C. C is 1 and P is 8, right? And when do I stop? When they're in the wrong order,
Okay.
right? Right? Up until now, the consecutive ones have been in the right order. So I'm saying, hey, everything's sorted so far, right? The minute they're in the wrong order, then I stop, right? So let's look at that. Here's the code. So what do we need? Loop invariant 3 is going to be down here later, but let's say, what do we need? We need to say that we have found R, and what's true about R is that this is the definition of R. Remember, the definition of R is the last place it's not sorted. So assuming nothing's a blank, R is going to be bigger than R plus 1, right? That's the definition of R. It's the last place it's sorted. It's sorted up to R. So then when you go to R plus 1, things get smaller, right? So we say we have found it. And so we're going to, when we see that, we're going to stop and we're going to know that the head is at R plus 1. All right, so let's bring in the code. Here, I guess I move things around here a bit. Here the code says, I know the value of C. And if P is less than C, right? If P is less than C, that's when we do this code, when P is less than C, right? But now what do we do on the else case, right? If P is less than C, then we I'm losing it here. P is less than C, then we move forward. But if P is greater than C, that's when we stop. And where do we go? Well, we drop out of this inner loop, right? So this second inner loop goes to line 14. So we go to line 15, which breaks us out of that inner loop. Does that make sense?
Yep. Professor?
Yep.
I was wondering, for the P is less than or equal to C, you said equal to each other. Is that like some type of swapping, or is that something else completely, like, or?
I don't think we're doing any swapping. I'm just,
okay.
right here, all our values are distinct, so we're not going to get two guys equal. But if they're equal, we're going to say that they're sorted.
Okay.
So this is just says, if P is less than or equal to C, then I'm consider them sorted. And if I consider them sorted, then just move past them, right? Because our goal is to move past the sorted things.
Okay,
right?
okay.
And when they're no longer sorted, when P is bigger than C, here P is bigger than C, that's when we're going to jump out of this loop and we're going to go down to line 15.
Okay.
Right? Everybody following this?
So what's that on line 13? What's the if condition there? The end if?
Oh, this if has this end if.
Sorry, what's that referring to? Sorry, can you repeat that?
This if here it says if P is less than C, else end if.
Okay, gotcha.
I think that's it. Maybe I got another if up there. Let's go up here to another if, and maybe, in fact, I need two end ifs. Maybe I don't have two, but here, somebody else said, what happens if I'm running along here, and C gets to be a blank. The head gets to be on a blank, right? That means that we've completed that we've run through the whole list, and every consecutive ones were sorted. So the whole thing must be sorted. And so we stop the entire program, right? Does that make sense? So there were actually in this loop 3 cases. Case 1, C is blank, right? Case 2, P is less than C. Case 3, P is greater than C, right? So there are 3 cases, and for each case, you have to say what you're going to do, right? Everybody get this?
Hey, Jeff, could you please have a look at the chat? There are someone they couldn't access to the assignment, the test, I mean.
So they can't do what? Chat.
So yeah, in the chat right now, some people saying that they can't access the test.
All right. Well, then let's see about that. Let's pause out of this. Let's go up here. Let's go to my homepage. Let's go to what course we're doing. We're doing 2001. Sometimes I forget what course we're doing. Let's go to the forum. And in the forum, we have all these various questions. I mean, at this point, if you have it and somebody else doesn't have it, mail it to them. But here, what are we? We're in test 2, I guess. Test 2, a message from me. Here, a message from me. Nope. Message from me. I guess this is a little confusing. Oh, here it is. So here it says, a few said they didn't get it. Here it is. Is it in here somewhere? I definitely uploaded it. Permalink. All right, it's not there. All right, so anyway, do you need it now or should I? I'm going to keep going and I'll post it somewhere else at the end of the test because we're in the middle of doing this now. But if somebody else wants to mail it to you, you can mail it. Oh, I know. Here, I know. Oh, I don't know if I have it on this. Let's see if I have it here. I don't have it on this computer necessarily.
Someone posted it in the chat.
Oh, excellent. Somebody posted it in the chat. Well done, somebody. Let's move on. All right. So let's go to the next line. Right? So what's the next line is if it's a blank, an exit from the entire program. And why do we do that? Well, because the pose condition is that they're all sorted, and we see that they're all sorted. Right? Everybody good?
Is it just me? I can't hear. So it's just probably me. Am I lagging?
No, I can't either.
Can't see what? You can't hear me, can't see me?
Oh, Jeff,
Yeah,
you
your
just
mic's on. We can
sometimes
see you.
break up occasionally.
Yeah, I think your mic's like fizzing out.
All right. Can you hear me now?
Yep.
Yeah. Yeah. No.
All right. All right. Well, hopefully the battery still works. All right. So where are we doing here? We are, we were moving our head along, which changing R. And if the head moves all the way to the blank, then the whole thing is sorted. So then when does it stop? It stops when the head gets to the blank. And when the head gets to the blank, we exit from the program and we get our post condition that things are sorted, right? All right, so now let's continue on to see what we need to do next. In order to do what we're going to do next is we're going to have a little bit of code, and then we're going to go into another loop. And the other loop is going to have loop invariant 3. So we're just about to get the loop invariant 3. And what does it, the loop invariant say? Well, it says that we found R, and we found R. And then it says the value that's too small, right? Which value is too small? The 1's too small, right? They got bigger and bigger and bigger. And then the value at R plus 1, right? So the value that's too small that had been in cell R plus 1, what did we do with it? we're going to save it into a new variable Q. All right. And where's the head? Well, the head is still somewhere in this range, right? We haven't changed that, right? So that's what we need to establish. So let's get some code. And I'm also going to deallocate P, but so I need to bring Q in, and Q is going to have the value of 1. All right. So that's what we've done so far. When we got all over here, then our new code is going to do that. And what's our code going to do it? This is the code between the two loops, right? We dropped out of that first loop that moved right, and now we're in a second loop that's going to be moving left. So here's the second loop. And what's the code between the loops? Well, it forgot the P. Remember, we saw the P disappeared, and it allocated new memory for Q. So Q came in. And what value does Q have? Q has the value that's at the head. Well, where's the head? The head we know is at line at cell R+1, and that's the one we want to be saving. So Q becomes 1. Everybody follow that?
Sir?
Yep.
You know how we had the value of P before? Wasn't P already the value at head?
No, it was the value before the head.
Oh, and then, well, then, okay then. Okay.
All right, we needed the value before the head. As when we're moving right, we need the value before the head to know that we're sorted. And we're moving left, we don't care if we don't have to check that we're sorted. What do we have to do is we have to remember this value that's too small. Why do we remember it's too small? Because we're going to put it where it belongs.
Okay.
Right?
Yep.
So we forget the previous value and remember the small value. All right, so that's our code there. And now we can talk about loop invariant 3. Now we're starting to run that next loop, that third loop. And what does it say? Well, there's a lot of talk here, but let's say what's going to happen. It's just what you expect to happen, right? We're going to start moving the head left. And what's going to be true is that the head is always going to be somewhere, right? It says the head somewhere. And wherever the head is, well, it might not actually be a blank. There might be a value there, but the value that's there, we don't care about. And all the values to the right have been shifted, right? Here, the 1, we read the 1 in, and so that left a space here. The 8 moved over to that space, and it left a space here. Right? Does that make sense? And when we go further, the 6 gets shifted over and leaves a space. Right? So that's what everybody see what we're doing here? So that's what the loop invariant says. The loop invariant says I somewhere, everybody that was from I to R shifted right, leaving a blank at spot I where the head is. And that's what the loop invariant says, right? And we're still remembering Q, right? Everybody good?
So we're comparing P to Q or Q to the head?
We haven't compared anything yet. That's in the code to come future. I'm just stating what the loop invariant is, what we're trying to maintain. I'm not talking about actions yet. It's just the picture. We went from this picture to this picture to this picture, and you need to understand what the pictures are.
But there was an action that you moved 6 to.
Yeah, the difference between this and this is an action. So later we'll talk about the code that makes that action happen, right? But at the moment, all we're getting is what is our loop invariant saying? The loop invariant saying is everybody has shifted, right? So yeah, here nothing is shifted. Here 8 shifted. Now 6 is also shifted, right?
So we're just shifting all the numbers.
That's what we will do in the future code is we'll shift. Right now we're just saying that's what every time we go around the loop, you shift one more number.
Okay.
Yep. Right? Why are we shifting it? Well, we're doing two things at the same time. We're moving left in order to find where the 1 belongs. But when we need to put the 1 in, everybody before it needs to be shifted. Right? Why do you need it to be shifted? Because, well, this spot where the 1 was, we don't want the 1 there anymore. Who do we want there? We want the 8 to move there. And then in the end, we need a spot to put the 1. Right? Does that make sense?
So are we gonna have blanks between the in the middle of the tape?
Well, as I said, it looks like a blank, but I didn't actually put a B there. So I'm not claiming this is a blank. I'm claiming it's a value that at the moment I don't care about. The chances are it's some garbage that, it's probably still the 6, right? It's something. I just don't. I'm saying we're considering it to be a vacant spot that we can do whatever we want with.
So at this moment, is it 1? At this moment.
I'm telling you, I don't care what it is.
Okay, fine.
Do you really care what it is?
Maybe. I don't know.
Well, you can work out what it is. I'm just telling you, it's right. It might be. I'll tell you, it's either a 1 or a 6, but I don't know or care which one.
So Turing machine can move all the cells between tapes. Is that how it works? Because I thought Turing machine cannot move shift the tapes.
Yeah. So I haven't told you yet the action, right? That's people keep wanting to talk about the actions, and one thing I'm talking about now is the loop invariant. And I guess I did talk about the difference between this picture. I'm trying to describe to you this picture. I'm trying not to describe actions. But how did I describe the picture? Well, I told you the difference between this picture and this picture, right? This first picture was the picture we got when we moved our head along here to here. And now what's the difference between these pictures is that things get shifted over, right? I'm trying not to, I said the word shift, so it sounds like I'm talking about a verb, but I don't want to think about how that action happens now. I just want to understand these pictures.
So loop invariant is just like an object that we need to accomplish?
Yeah, it's a picture that we need to accomplish.
Okay.
Loop invariant is a picture of what's true when you're at the top of the loop. And I'm claiming what's at the top of the loop is, well, I still remember the value that's small and that I'm moving. The head is somewhere. Everybody from where the head is up to R has shifted over, and the spot where the head is, I don't care the value there. That's what the loop invariant is. And that's these pictures, right? Does everybody understand the pictures and kind of why we're doing these pictures? All right. So now let's choose 2 of the pictures, 2 of the loop invariants, and we're going to figure out the code, how to move from one to the other. All right. So suppose we're in this picture and we want to make this picture, right? So we need to think what the Turing machine can do. It can move the head, it can read the value at the head, it can write a value at the head, it can move the head, right? So what are we going to have it do? Well, the head's here. So what it's going to do, look at the code here. Its first thing it's going to do is move the head left, right? It moves the head left. And then it's going to allocate memory for P. And what is it going to do with P? It's going to store the value at the head. It's going to store the 6 in P, right? And it's going to read that value at P. And so it has 6 now in P. And then it's going to move the head right again, right? It's going to write the value P into the cell. And then it's going to move its head left again, right? So that's how we get from here to here. Everybody follow that code? Right? The head's here. I come over here. I read the 6 into P. I come back here, I write the value of P, then I move the head here, right? That gets me from this picture to this picture. Everybody buy that?
Sir.
Yep.
So like so when we reallocate memory for variable P, it's still going to be at the spot where we deallocated the memory, right? So you know how before we had to deallocate memory for P?
Yeah.
So it's the head still at the spot where we deallocated it, right?
No, the head, we're not deallocating the head. I have a blackboard, Pooh Bear's blackboard. I can write anything on Pooh Bear's blackboard I want. So maybe there's not, at some point we had P written on the blackboard, and then we erased it, and we said P's no longer on the blackboard.
Okay.
Now I'm going to say, I need P on the blackboard again. So I'm going to have space on my blackboard to write the value of P. And in the value, and what do I write there? I write the value 6 there on my blackboard, right?
So we can write P wherever we want?
You could. So what can a Turing machine do? It has a blackboard, and it can write anything on the blackboard that it wants. Okay. And what does that really mean? What it really means is that the Turing machine can go into any state that it wants, right? And it can name a state, right? So let me give you a little hint here, right? If my variable P has the value 6, and I'm in line, say, 29, then what state am I in? I'm in the state, I'm in line 29, and I remember that P equals 6, right? Okay. That's the name of my state.
Okay.
Right? Does that make sense? Everybody write that down quickly. I'm going to have a state whose name is line equals 29, P equals 6. Right? Does that make sense? So when I say moving the head is one issue, right? That's a different issue. But what do I mean by allocate memory is I'm now going to have more states so that I can write things on my blackboard. I'm now going to have, and when I put a value in the blackboard, then it says that means go to a state that knows the value that's at the head. It knows I'm now in a state that remembers 6, right? Had there been a 12 here, I would have gone into state that I remember that P equals 12, right? So I'm remembering from what we see here now, actually from here I'm remembering 3 things, right? What are the 3 things my state tells me? Tells me what line I'm on, it tells me the value of P, and it tells me the value of Q, right? So that all needs to be in my state. Right? Everybody good?
So in this case, like, would you actually put the value of P and Q in the statement?
In the state. Your state needs to know the value.
Okay. But then I thought we cannot put any values. I thought we were only allowed to put like a C or P, or like a C prime, P prime. You know what we talked about yesterday? Instead of putting actual values like 1 or 2, 3.
It all boils down to values. P prime always represents a value.
Okay, so that can be a constant number then.
All right, so just to warn you here, my earphones say that the battery is low. So we'll see what happens. We might have to go to the non-earphone mic. Everybody follow what we're doing here? And we're not supposed to be understanding Turing machines right now. We're supposed to be understanding the Java code, right? So the Java code is saving, right? Everybody understand the Java code here? What we're doing?
So just a clarification, Professor.
Yeah.
You mentioned line 29.
Yeah.
So what line, so do you write the line that we write a value in the cell, or do we write the line that the head moves for the state?
it's, I didn't quite get the question, but if I'm just about to execute line 29, I'm in the state, I'm at line 29 means I haven't executed 29 yet. I'm about to execute 29.
Okay, gotcha. I just
Right.
wanted to confirm because from what I remember, we only write the state transitions, right? So I was having a bit of confusion. Which line should I write for it to be the state transition? Would it be when the head moves? Would it be when you write a value into the cell? Would it be at the starting of the allocation of the memory?
All right, so we're getting off topic. We're
Yeah.
getting into Turing machines.
Mhm.
But if the Java program is about to be, suppose the Java program is about to execute line 29. All right, and suppose P equals 6,
Okay.
and suppose Q equals 1.
Mhm.
Right? Then what state is the Java program in? It's in the state line equals 29, P equals 6, Q equals 1. That's the state the Java program is in, right?
Okay.
So what state is the Turing machine in? It's in some state whose name, right? The Turing machine doesn't actually have variables. So the Turing machine is in a state, and all we can do with that state is give it a name. And the name of the state will be, I'm in line 29, P has the value 1, V has the value 6, and Q has the value 1. That's the name of the state.
Okay, gotcha.
Right? Does that make sense?
I think so. So basically what you're saying is the line reference is more when we write the value in the cell. That's the line reference you should be referring to for the state.
No, I didn't say anything about writing the values.
So you're saying
talked
here,
about
line
what state I'm
29,
in.
write P into cell, right? I
So
understand
ignore
that you
this.
can't actually...
Ignore this code. Ignore this code.
Yep.
I'm just saying, if I'm starting to execute line 29, what state? It's trying line 24. What state I'm in? I told you what state I'm in. I'm in the state line equals 24, P equals 6, Q equals 1. That's the state I'm in. Right. So then we have to come up with a delta function. The delta function is going to say, if I'm in that state and I'm reading some character from the tape, what state will I go in next? What character will I write on the head? How will I move the tape head? All right, so I want to leave that right now because we're off topic. You're focusing on Turing machines and I'm focusing on Java programs. I'm only committed to right now to tell you how to do Java programs. If you want to know how to do Turing machines, we can do them after. All right? Let's focus on what does our Java program do? All right? So everybody get what the Java program is doing. Right? I'm trying to get from here to here. How do I get from here to here? I move the head over. I read in the value of 6 into P. I move right. I write the value of 6 onto the tape. I move left again, and I get this picture. Right? Everybody good? All right. So let's see when we're going to stop. Right? We're going to keep doing that until what? When do we stop? We stop when the value 1 needs to go in the blank spot. Remember, our picture is that there's a, quote, blank spot where the head is, right? So when we are going to do that, when we stop, when that's where the 1 goes. And why does the 1 go here? Anybody know why the 1 goes here?
Smallest value.
Why didn't the 1 go here?
Because it's less than 6.
Because it's less than 6, right? Why didn't it go here? Because it's less than 5. Why does it go here? because it's bigger than negative infinity, right? And what is, right? And what is this value? Remember, we went over here and we came back. What's that value? That was value P. So, right Q. So at some point in the code, we are going to, up above, I'm going to write Q in the Q into this blank space. And why do we do that? Well, there are two reasons we do that. The one reason is I am going to be trying to save space. So I'm going to allocate and deallocate things to save memory space. But the other reason to do that is, well, Q might go there, right? So I'm going to take my Q and I'm going to write it in there and say, hey, it goes there. So there it is. I write it in there. And then, right, so let's go through the code just as it was before, right? I write Q into the cell. Then I move left and I pick up P as negative infinity. Then I move right again, right? So that's what we did. And what we were about to do is write Q here, write P here, right? Because we're shifting the value over. But before we shift the value over, we're going to check, hey, which is which, right? If P is less than Q, then what does that mean? It means they're sorted, right? Right? So our picture now looks like this. We came down here, our picture looks like this. And we're in 20 line 26, we say, hey, if P, we have the value of P, if P is less than Q, and what's Q? Q is the value we wrote, P is the value we just read, right? So if P is less than Q, then we wrote Q into the cell, Q is where it's supposed to be, and we will stop. And how do we stop? We finish this bottom loop and we go back up. In fact, what we're saying is, look at, now one's where it belongs, right? So we can go right back to the top of the main loop, right? The top of the main loop is line equals 3, right? Here is, remember loop invariant 1 is that everything is sorted and the head is somewhere, right? And in fact, everything is sorted, the head is where it is, and we know the previous value, right? So I know the previous value, and I know everything is sorted. So I can just go right back up to the top of the main loop. Does that make sense? All right. So now, right, and I have some new R. I have some new R and I've made progress, and everything is good, right? So is everybody understanding this code? This code here should work just fine, right?
Yep.
Now, I'm going to add some new lines, and what are the lines I've added? Is sometimes I deallocate memory and sometimes I reallocate it, right? So what's happening on my blackboard is sometimes I have values on my blackboard and I erase them, and then I put new values on my blackboard and I erase those, and sometimes I'm going to have P on my blackboard and sometimes I'm going to have Q on my blackboard, all right? And my battery is low, but when it dies, then we'll have to listen to me some other way. All right, so just as a look at here is right up here, I had the value of Q. I wrote Q into the spot, and now I don't need to remember any Q anymore because I've written it down. So then I can forget Q, and then I can allocate memory for P, and then at some point I forget P. And I remember Q. All right? So it's this forget. And so you can worry about yourself is to make sure we're allocating and reallocating enough so that we always have the right value. All right? We're not going to go into that detail. Any questions about all of this? That's the entire code, right? Here's it written down. Here's the next page, right?
I have a question.
Yeah.
Necessary at the start to let p equal negative infinity?
Yeah.
Because in the first loop, can't we just assign p to I minus 1? And then that would, and while accessing the tape, and that would account for negative infinity?
Yes, we could. Here, how did we, right? We had to establish the loop invariant. And the way I established the loop invariant is by setting p to be negative infinity. Instead, what you could have done is you could have gone right and, well, what value is going to be before the input, right? It's going to, I'm saying the value before the input is going to be negative infinity to make your life easier. If we didn't have this precondition that before was negative infinity, then you're going to have to do some work to make all this work better. And I did this to make your life easier. So does that make sense?
Yeah, that makes sense. I got it.
I just have a question.
Yeah.
So in some cases, like for example, when we deallocate in memory and stuff,
right?
We enter into a new state when we deallocate. It's because we're going from where it have it and then it doesn't have it, right?
Yeah.
So but in those cases, the head doesn't move, right? Because it's just forgetting like what it is. So can you enter a new state while not moving the head?
All right, just to let you know, I'm in the speaker you don't like. Can you hear me?
Yeah.
Okay. So you're starting to talk again about Turing machines. So does everybody understand the Java code well enough?
Yeah.
Yes.
All right. And the truth is, as I said, you don't actually even have to understand it, right? All you have to do is say, what state am I in, and move forward. All right. So let me tell you that before you ask more questions, let's come over here and come over here and scroll down here. Anybody who wasn't here the other day, yesterday, see this little face there? That face is the face of, it's a video that was recorded this term, and it's a long video. Holy cow, is it really a 3-hour video? Were we talking for 3 hours? No wonder I was so tired. Anyway, it starts with how to do, what steps to follow in order to convert a Turing machine, convert a Java program into a Turing machine. And it goes slowly through this example here. So if you're getting lost, then watch that video. But let me give you a short version of it now. Right? So this is on your test question, right? I wrote it down to something's buzzing, but whatever. All right. Oh, here, this is on your test question. So I'm going to remember that various people ask questions about Turing machines, and let me see if I can answer some of your questions by going through these steps. All right. So I would start with the start state, right? Start at the beginning of the code. And so in general, what you're going to do when you're running through the code, you want to say, I'm somewhere, and how far do I want to execute the code? All right. And there's two options. The one option is that you run the code until the head moves, right? You can't run it further than that, right? Because when the head moves, then things change and the Turing machine needs to take a step, right? So definitely stop running the Java code when the head moves. But sometimes, and do that, generally do that. But sometimes it's a nice, you also want to end up in nice, clean places, right? So as a hint, a nice, clean place is at the top of a loop, right? Because why is that nice? Well, because at the top of the loop, you know the loop invariant's true, you know how to go forward. So top of the loops are places we want to go, right? So in fact, I'm not sure if this is absolutely true, but when you're running the code forward, you're going to either go forward until the head moves or go forward till you get to the top of a loop, right? So those are two places to run forward. So the first thing you're going to do is I'm starting my Java program and I need a start state, right? So what's my start state going to be? Well, I don't have to start at the start of the program, right? I can start running the program until I'm somewhere where I like to be. Where will that be? As I just said, I'm running it until the head moves or until I'm in the top of a loop that I like, right? So that's what we do. And we get our start state. And what is, every time a state, what does a state say? It says, the name of the state is always, what line of code am I about to execute? If I'm in line, if it says line 9, then that means I haven't executed line 9 yet, but I'm about to, right? And then it lists all the information that's on the blackboard, right? Pooh Bear has a blackboard. It may be storing P, it may be storing Q. It never stores C because C is the character that's on the, as I see at the tape, right? But it's storing P, it's storing Q, right? So that's what you write down in the state, right? So now you have to fill in a block of the table. So you start with, what line of code am I working on, right? Well, maybe I'm working on line 9 or some line I'm working on. Why is I'm working on line 9? I'm not going to work on all the lines. Why I'm looking at line 9 is because at some point I stopped and I was on line 9 and now you have to continue again, right? So you're somewhere in the program and you want to say, okay, I'm on a particular line. Now I'm on that line and so I know what state I'm in, right? If you know what state you're in, then you say, what happened? So you start running the Java program until now we're going to run it until one of three things happens. Maybe the head moves and then you have to transition the state. Or maybe you get to the top of the loop and then you say, hey, this is a nice place to be. Let's rest here, right? Or maybe, here's another funny thing that could happen, is I could get to a case, right? Maybe the case is that P prime is less than C, or maybe the case is that P prime is less than Q prime, right? Now I don't know which way the code will go, right? So I roll back to where I started. Remember, I started on, say, maybe line 9. And I said, I'm on line 9. All right, consider what's true at line 9, right? Maybe I'm at the top of the loops. If I'm at the top of the loop, that's nice because then the loop invariant tells me what's true, right? And then I start running the code and I see that there's more than one cases. So choose a case, right? I'm now going to do this case, right? So if I'm doing this case, now what am I doing? I know I'm at line 9 and I know I'm doing a case here, right? So if I'm doing that case, then what state am I in? Well, I'm clearly in I'm in line 9, right? Because that's what I said. But also there's some restrictions on P and Q. Or if I'm in this case, then there's that restriction. So there's some restriction on what state I'm in. So if I say, then I say, if you're in this one of these states, now what do I do? All right. So here I'm in some state. I know I'm in line 9. I know the value stored on the blackboard, right? So so what am I going to do? I'm going to say, oh, now what character am I reading at the head? It could be a generic C. Is it in negative infinity? Is it in the range 1 to D? Does it have some restriction on it? All right. What are the C's I'm considering? Right. So that tells me what block of the table I'm filling in. There's a range of states that I'm filling in. There's a range of characters that I'm filling in, right? So then, now that I know all of those things, then I know what state I'm in, and I know what character I'm reading. So then I start running the code, right? And as I run the code, it's going to go past the condition, but that's okay because I know which condition we're doing. And then I keep running the code, and as I run the code, it's going to do what? It's either going to get at the top of a loop, or it's going to get that the head moves, right? And then I say, okay, now what's true? Well, what line of code am I about to execute, right? Maybe line 12 moves the head. If line 12 moves the head, then I'm going to run the code for line 13. But I'm not going to execute 13. So 12 is going to be executed because I moved the head. But now I'm about to execute line 13, right? So what state am I going to? I'm going to, I know line 13, and now tell me everything that's on the blackboard, right? And then what do we have? Then you just write down the transition function. If I'm in this state and I'm reading this character, what state do I go into? What character do I write on the tape? If the code says write something on the tape, what am I writing on the tape? And what direction am I moving the head? All right, does that make sense?
So for example, let me say we at the end of a loop, right? And the head, and we reach the end of a loop, but the head hasn't moved. When we return to the top of the loop,
then you go to the top of the loop.
Yeah.
Then what line are you on? I'm about to execute the top of the loop.
Right. And if the head doesn't move, how would you represent that in the change of states, for
Well,
example?
if the head doesn't move, then what direction are you going?
Nowhere.
Well, you just use stay.
I was using stay. Remember? Right, left, stay.
Stay. Okay.
Right?
Okay.
So are we allowed to use stay?
Yeah. So maybe I should rewrite this page so that it talks about loops. So I'm giving you more advice in general here. I think you want to keep running the Turing machine until one of two things happens. You have to be able to get past cases. If you get an if statement, you want to go past those, but you need to have a block telling you which case you're going. And then where do you want to run? Well, you want to run either until the head moves, or you're somewhere really pretty that you like to be. And where would that be? To me, that's at the top of a loop. So let's try to get everybody's answer to look the same. And the way you would get your answer to look like my answer is run the code until either the head moves or that you're at the top of a loop. Right? Does that make sense? And that's top of loops are great because you know the loop invariant's true, and you need code to start from the top of the loop, right? So, I mean, the nice thing about going to the top of the loop is that you don't have to write more transitions, because when you got to the top of the loop, you already wrote the transitions for the top of the loop. So if you go back to the top of the loop, you don't have to rewrite the Turing code to handle the top of the loop, because you've already done it, right? Does that make sense?
Sir, I have a question.
Yeah.
So when we have halting cases, like when something is a halt, can we just make these separate, like in the answer, like make them separate, like just on the side, and show like the cases where we have halt?
So if your Java code, there's one place where your Java code exits the program, and when you do that, you transition to the state halt.
So there's only one. There's only one line where it does that.
I think so. Do you see other places?
I thought there was 2 places where it happened.
Yeah, I think so.
So here it says if C is a blank, then it exits from the entire program.
Yeah.
Yeah, so that's one case, and then the other case is after, when we go to into the second loop.
So what line
number? Line number, I think it would be 24, or like after 24, we compare here, and then when we compare, it says go back to line 3.
Yeah.
So we go back to line 3, and then that's another case.
No, that's not exiting.
Oh,
line
sorry,
3
that's
is the top of a loop. Line 3 is the top of the loop.
Yeah, sorry, my bad. I meant like at line 24, since we're moving right and we're learning new information, there's a possibility that when we move right, it's a B.
Yeah, it could be.
But I'm not testing it. The code's not testing it.
We test it when we go to the if statement though, and then if we do make the value, we move the head right, and then we let Q denote the value at head, then Q would be B.
All right, so I'm claiming if you ever get something that you don't expect, right? Suppose I read the value at the head, and then I do some comparison, and it's a blank. Then if my Java program doesn't deal with the fact that it might be a blank, then what the Java program would do, what happens if I compared, if I was running Java and P was a blank and Q was a 7?
It would throw an error.
It would throw an error, right?
Yeah.
So what should you do in your Java code, in your Turing code? You should panic.
Okay,
right?
I understand.
What I do,
Thank you.
So here's another thing, is you want to fill out the entire table, right? You want to say for every state and for every character I may be looking at, you want to say, what is the Turing machine going to do? And so go through and run the program like we're talking, and then look at the table and you see what entries of the table have I not done, right? And one of the entries might be, and those would all be panics, right? So for each of those, somebody said they want to come in, and then they went away. I don't know how to get them in anymore. Hope that maybe they're in. I don't know. It said let somebody in. All right, everybody get that?
I was a little bit confused when you were mentioning the stay cases. So we can use stay when we're at like when we're going back to the top of the loop.
Yeah, yeah. In fact, right. So here I said go to line 3. Well, line 3 is the top of the loop, right?
Okay.
So what I was telling you in these instructions over here is you run the code until the head moved, but the head didn't move, did it?
No.
Yeah, but I went to the top of the loop, and do I want to really worry about the top of the loop right now? No, let's worry about the top of the loop at the top of the loop. So when I go to line 3, well, I'm going to go to the top of the loop, but I'm not going to move my head, so my head will be stationary.
Okay, because for this case, I just went all the way to the top and looked for the next time it moves and did that.
Right. So that would be, if you're wanting the most optimal Turing machine code, that's what you should do.
So would it be right though?
It would still be. It would be more right than my solution.
Okay. Okay. Thank you.
But you might want to. Being more right isn't necessarily mean that the TA will like it, right? So if you haven't written it up yet, you might want to go for looking. If your answer looks identical to my answer, the TA will just give you perfect, right?
Yeah.
If you make your answer different than my answer, then the TA will have to work, and you don't want to make the TA work. Right?
That's true. That is true.
So let's all go for keep running the code until either the head moves or you get to the top of a loop.
Okay.
And you'll make your life easier too.
Sir, for the number of states, since you didn't give us a specific output, you want the total possible states?
We definitely want the total possible number of states, right? And remember, the number of states can depend on D, right? Because remember, in our last test, the boss gives you D, which is the range of the boss gives you D, which is the tape alphabet, and so the number of states can depend on D, but it can't depend on N. So all you have to do is go through your states and count how many states there are.
Okay, got it.
Right? And then the next question is, these are the lines that allocate and deallocate memory, right? So if you delete all of those, I'm asking you what changes, right? And then we do running time. All right, everybody good?
Sir, can you explain the running time of a Turing machine?
All right, so what does a Turing machine do? Every time you apply the delta function, it might move ahead, it might change states, it's going to do one or the other. It has to do one or the other. That's a time step. So you want to count how many time steps there are. And maybe I didn't say this here. I got big O's here, right? So everything, in fact, I said, what is the big O, right? So you don't have to be anal about counting every last, you might as well be anal and count every last state, but you don't have to be anal and count every last time step. We want to, is it big O of n squared? Is it big O of n cubed, or n to the fourth, or did we somehow go faster? Is it somehow n?
Sir, I just have a question.
Yeah.
For saying how many states does your Turing machine have? So can we just say exactly the number and that's it, or we have to exactly show you in steps how we got it?
I would say, as a rule of thumb, if you give, here's true about any test in the world, really, is if you give the perfect answer, then the TA will be very happy and give you perfect. But if your answer is wrong, then if all you give is the answer, it's hard for if you just answer there are 38 states, right? Then I, as a TA, will go back up and look at your Turing machine and see how many states there are, right? And if it's 38, okay, you got the right answer. But if it's not 38, then I don't know how to give you part marks.
Yeah,
right.
But I think did you kind of give us a hint on how to count the states in here?
Yeah, we did this in earlier slides. The way I would do it is I would look at each, you have these blocks that are filling in the table, right? And you have these states. So you look at all the states that are line 1,
Yeah.
right? Look at all states that are line 1. How many are there? So I would write down here, I have 5 states for line 1. I have 10 states that are line 2, right? And then you add them up.
All right, I see how you made it. So you just broke it apart to explain the TA, how the answer is made up.
Yeah.
How did we get the number of
Yeah.
states?
Yeah, that's what I would say. I would say I have how many states do I have for line 1? And I might say, why do I have that many states?
I see how it goes.
Right?
I see how it goes. Yeah. Okay.
So I just have a question about the states as well. So because it depends on D, do we have to write the number of states in terms of D? Because we don't exactly know. Okay,
Well,
we don't exactly know where D is.
No, you're not allowed to ask that question. Dude, does it depend on D?
Oh, okay.
So nobody heard that. He didn't just give the answer to that question. Well, I mean, it's obvious it does, right? All right, everybody good? And
Professor?
I really wanted to give you another harder question, but it looks like you guys are struggling enough with this one.
Professor?
Yes.
I just had a quick question now. Where would you put the conditions? Like, you know how we have if P is less than or greater than C?
Yeah.
Yeah, where would we put the conditions when we put it in terms of the Turing machine? Like, would you just put it off to the side saying P is less than or greater than?
Yeah.
Less than or equal to C?
Yeah. So there's a range. You say, the way you define a block, how do you define a block of the table? You have to tell me which states I'm handling and which character C I'm handling, right? So on the left, you would say, I'm currently handling all the states that have the form line equals 7 and P prime equals yada da 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 da, right? You tell me which states you're handling, and that's where you put the condition.
Okay, thank you.
Oh, so and just to be clear, because I wasn't really here for the last class. I wasn't here for the full lecture.
Yeah.
So it's not, you can write it, the transitions as a list, right? It's not actual table before, no. You can just write it as a list.
Yeah, it's a list.
Yeah.
It's a list of blocks. For
Yeah.
each block, you say which states and which C am I handling, and then you write the transition for that block, and then you do it for the next block.
Okay, okay.
Right? Because you can't do the whole table, right?
Yeah.
The whole table's huge.
I have a question. So when we have the condition P is less than or equals to C, so we're gonna go through the else if statement that you give us, right, in the code, and we're gonna keep going. So when we want to exit this, when we want to say that this else if does not work anymore, so I'm just like asking, because how do I make it? How do I write it for the TA? Like how he wants it? Should I like just make a separate, like make it separate on the side and just say like this is the condition when we have P less than or equals to Q?
All right. I think I just answered that question. So let me answer it again.
Yes.
Your answer will have a line or a few lines per your goal is to fill in this table, right?
Yes.
So with every line, you're not going to give me a whole table. Every time you fill in a block of the table, right?
Yes.
So when you're filling in a given block, you tell me what's the range of a block will always be the same line number. So it's always line equals, say, 10, and then what's the range of P prime? What's the range of Q prime? What's the range of C, right? That will tell me the block. And
where you mean where I'm working at? Where is
which block and am I working on? And that's where you say, I'm currently working on the block where P prime is less than C.
Yep.
Right? That's
so now when I want to exit this part, when I want to go to the second block, right?
No, each block is its own block.
Yeah,
Now
so
you
like
do
I
another
just
block.
write it after. Like I just write it after. That's all I
Yeah,
do.
just
Like
write
it's
it
like
after. So list
okay.
the blocks.
Yeah, I see how it
List the
works.
blocks.
Because we have different if statements. Like, and this is why I'm asking. Okay.
Yeah. Yeah. Well, one block takes you to another block, and then the other block takes you to another block, right? So the Turing machine runs.
Yeah, obviously, because if the else if doesn't work, then we can't go. We can't keep going. And that was one of the questions you asked.
You do need to fill in. Remember, I said make sure you fill in the entire table. So if you have one block that's handling p prime less than q, you need another block that handles the other case.
Okay, and they go in order. Okay.
Well, I put them in order. You know, I think if you follow my instructions here, really, I think if you just kind of understand what I'm doing here and you follow the instructions that I just gave, not only will it be easy, but your solution will be letter by letter identical to my solution, right? I've really told you how to write down the answer, right? So there's absolutely no reason for everybody's answer should be identical.
Okay.
Right?
Yep.
I've told you exactly how to do it. So you just do it and life will be easy.
Jeff.
Yep.
I'm a little confused about what input tape we'll be using.
You've lost me here.
As in, we need to use an input tape to follow the code, right?
Yeah,
So,
no, you're writing code that needs to work no matter what the input is. Right? That's why we have cases. Right? We have cases because I don't know what the input will be.
Yeah. Okay,
You're writing a Turing machine that will work no matter what the input is.
Gotcha.
No matter what in is.
Thanks.
How's everybody doing? Everybody good?
Sir, just one more question. When I use Q prime and let's say C prime, do I have to indicate for you like before how the line starts, you know, what these mean? Like Q prime, C prime, what are they related for? Like, you know, yesterday in the example you showed us, you just say like you just tell us what like 01 stands for C, for example. Like I have to show that too, right? Like before the line starts. Like X is
the delta
X
function.
Yeah.
The delta function will say I'm in line 10 and P equals P prime.
Yeah.
Right? So I know P prime is meaning the value of P.
Yeah,
right?
because sometimes in the lines you say assign a new variable. So that's where I make, for example, Q prime. So this is where I'm using it. So I don't have to mention what does Q prime relate to, right? Like
you don't give me anything that looks like Java code. You're only giving me delta transitions.
Okay.
If it doesn't look like you're giving me a delta transition, don't give it to me.
Sir, I have a question. So by that, we can't use a array notation to represent like read something from some part of the tape?
No. All we're doing is what's the name of the state that I'm in? What's the name of the state that I'm going to? That's all you're allowed to do. No arrays, no Java code, no nothing.
So the values for the variables, would they be arbitrary? Like P prime and then Z prime?
No, you tell me what you have to tell me the names of the states that you're talking about. Forget about the Java program now. When you're describing a Turing machine, you tell me the names of the states, and you tell me for each state, in each character I might read, you tell me the name of the state that I go to, right?
No, I'm actually talking about the character that we're reading from the tape.
Yeah, so you tell me I'm reading some character, maybe I'm reading a 0 or 1 or a 2, so I'm reading some C where C's in this range.
Okay, so it's some arbitrary C.
Well, it's not completely arbitrary. You're not reading an elephant. C can't be an elephant.
Yeah, it's an integer, right? Yeah.
All right, should we go?
Jeff,
Yeah.
one last question. For when you say deallocate, does that mean it no longer exists or that it's
Erase
empty?
it. In the Java program, I erase it off the blackboard.
Okay.
The Turing machine will no longer know it.
Got it.
Hi Jeff, just a quick question. Like you said on yesterday's lecture, like if we write down some p prime, we will lose mark for it unless we give you some specific value. So there's some situations we can't come up with specific values. So are we able to give you some kind of range?
Yeah, that's what it said. You're filling in an entire block of the table. So you're giving me ranges.
Thank you.
Hey Jeff, my partner just told me that he dropped the course. What should I do now? Should I just do it alone, or is there someone else who's alone?
You're if you want, I can find someone for you. I've kind of lost. I think I got an I got an email from somebody that they needed a partner, and it might have even been from you. So if you send me an email, then I will link you or try to link you with somebody.
Okay, yeah, I did send an email, so.
All right, so then it's probably you, and so I don't want to link you to you.
Okay. All right, so for now, I just work alone then?
Yeah.
Okay. All right, thanks.
Sir, what if you haven't heard from your partner till now?
If you haven't heard from your partner, then the guy who was just talking, hook up with him.
Okay, cool.
So you two, what you need to do right now is write in the chat who you are, and you are now partners.
Okay.
Hey Jeff, what if my partner haven't shown until now?
Now there are three of you. Now you're odd again.
No, I have a partner, but he doesn't show up.
He hasn't talked to you at all?
No, not at all. Just
Well,
one
you don't
sentence
have a
through the
partner.
email.
You don't have a partner, so you're like those other two people.
Okay.
So if people don't hear from their partner, they can just team up with whoever doesn't have a partner too?
At this point, if you haven't heard from your partner at 4 o'clock on test day, then your partner doesn't exist.
Agree.
Professor, just a quick question regarding D for the time complexity.
Yep.
Can we just talk about generics of a Turing machine and time complexity, or do we have to talk specifics about the algorithm?
You
Insertion
need to
sort
know
of.
what's the running time of your Turing machine.
Okay, so we have to talk about whatever the answer is for this particular Turing machine.
Yes.
Okay, gotcha. Thank you.
And it's very short. You say, oh, the Turing machine does this and it does this, blah blah blah. Look at it's clearly this running time. That's my answer.
Okay. Okay. Thank you.
You're not doing any complex analysis. You're doing just you give the answer, you say it's order into the fifth. Why is it in the fifth? Well, because I do this n times, and for each of those I do this n times, and for each of those I do this n times.
Professor, can you just go to page 174 for 1 second?
174.
Because I just want to ask this because it's just in my mind. Like I can't. Like I just want to know.
174 would be that one. Is that good?
I can't see it.
Oh.
I'm still. I can see only page 324 still. Okay, now it's moving back. Okay.
Oh. All right. Okay. I didn't do anything, so maybe it just caught up. I don't know. You on the right page?
Page. Oh, did it go back because you updated? I'm just looking where you are. We was actually writing the answers for this question. I'm just looking for that.
Down here?
Because I think you added the new pages. This is why this is not showing. Because like
Yeah.
on mine, because I have the previous one.
Yeah.
Either you go up. Could you go up? I think it's up.
I moved, and why isn't it keeping up with me?
Yeah, I can't see it too. I'm still seeing page 174. Okay, now it's moving.
All right, that was a while ago. I don't know why it's taking so long to update.
Yeah. Here. Okay, you see where it says for every C and C prime goes to 0 and 1, the first line?
Yeah.
Okay, do we need to say that when we have cube, Q prime, do we have to actually show you these stuff on the side before we write the line?
This is a fine question. See, everybody see written here?
Yes.
That is exactly what we want to do for a block. I want to say, what state am I in? And there's a range here, right? The range might include P primes and Q primes. It might, and then what character am I reading? There might be a range here. So you specify the range to specify which states am I talking about and which characters am I reading. And then you say, for that range, for that block, if I'm in such a state and I'm reading such a character, then where do I go?
Okay, so we just have to specify this. This is all I want to know.
Yeah.
We have to say the range. Okay.
That is your answer. Give me a range, and then for that whole block, this is a range on a block of your table. For that block of your table, what does the delta function do?
And you're gonna have this range in every time there is a Q prime and a C prime.
Every block you need to do this. There'll be every block will have a different range. And then in the end, what do? You say, look at all these ranges, right? Have I filled in the entire table, right? For every state that I've named and every character that might be on the tape, have I said what the Turing machine will do?